The Large Hadron Collider, LHC, stands as one of the marvels of modern science. It is widely regarded as the largest and most intricate machine ever built by humanity. Yet some physicists propose that a subtle flaw may exist within the very fabric of reality, so minute that centuries of experimentation have missed it. The next-generation particle collider is being designed specifically to detect this potential anomaly. In professional terms, this error in space-time would manifest as a breakdown in fundamental symmetries of nature, particularly violations of Lorentz invariance and CPT symmetry. Lorentz invariance underpins special relativity, asserting that the laws of physics hold true for all inertial observers. CPT symmetry, combining charge conjugation C, parity transformation P, and time reversal T, is a cornerstone of quantum field theory. Any confirmed violation of these symmetries would represent a groundbreaking discovery, providing direct evidence for physics beyond the standard model. Such an observation would likely demand a wholly new theoretical framework, potentially tied to quantum gravity at energy scales approaching the Planck energy, around 10 to the 19th GeV. Here lies the challenge. Data from the LHC has consistently validated the standard model with extraordinary precision. No convincing signs of Lorentz violation or CPT breaking have emerged. If a flaw in space-time exists, it must be extremely subtle, requiring sensitivities far beyond current capabilities. This is precisely why the next collider, the Future Circular Collider, FCC, is necessary. The FCC is envisioned as a massive underground ring, approximately 90.7 kilometers in circumference, straddling the France-Switzerland border near Geneva. Its implementation is planned in stages. Stage 1, FCCE, is an electron-positron collider aimed at high-precision studies of the Higgs boson, Z boson, and top quark, expected to operate for roughly 15 years. Stage 2, FCCE-STH, will be a proton collider reusing FCCE infrastructure, targeting collision energies of 100 TeV, nearly an order of magnitude higher than the LHC's current 13.6 TeV. This ultra-high energy phase could provide the sensitivity needed to observe effects of a spacetime flaw. While the FCCE Majalton H8 may be required to reach Planck-scale phenomena, detection could occur decades earlier. FCCE, although lower in energy, operates on the intensity frontier, achieving unprecedented precision. Minute violations of Lorentz symmetry could appear as subtle deviations in standard model parameters, effectively giving scientists a 20-year early warning before FCCE-H8 comes online. The search for space-time anomalies is not random. It is guided systematically by the Standard Model Extension, SME, a comprehensive phenomenological framework that integrates the standard model, general relativity, and all possible operators capable of perturbatively breaking Lorentz or CPT symmetry while remaining coordinate independent. The SME serves as a roadmap for experimentalists, classifying potential violations and linking CPT anomalies directly to Lorentz symmetry breaking. It also includes operators that violate Lorentz invariance while preserving CPT symmetry. In the SME, Lorentz and CPT violations are introduced via fixed tensor-valued background fields that permeate spacetime. Unlike dynamic quantum fields, these background fields are static. When an experiment is rotated or boosted, the fields remain unchanged, producing measurable effects. This introduces a preferred frame of reference within the universe, violating one of the core assumptions of special relativity, a fundamental asymmetry in space and time. If a spacetime error is discovered, its signatures would be subtle and persistent rather than a single particle detection. For example, Lorentz violation would distort the motion of charged particles in magnetic fields, altering the eccentricities of their orbits. In a perfectly Lorentz invariant system, these orbits behave predictably regardless of the laboratory's orientation. In the presence of symmetry violation, particle motion would shift, depending on the absolute orientation of the lab relative to the fixed background fields filling the universe. The extreme precision of future colliders like the FCC will be essential to measure these tiny deviations and reveal the hidden structure of spacetime. By carefully analyzing how particle orbit eccentricities change as an accelerator rotates relative to distant background fields, physicists can place limits on specific SME coefficients that would otherwise be unconstrained. Achieving this requires detectors with tracking and calorimetry systems of unprecedented precision. Perhaps the most striking evidence of a spacetime flaw would be the observation of processes currently forbidden by the standard model and established conservation laws. Violations of Lorentz invariance fundamentally modify the relationship between a particle's energy and its momentum, the dispersion relation. If this relation is altered, high-energy particles could exceed the conventional speed of light, leading to phenomena such as vacuum Cherenkov radiation. In this process, charged particles emit photons spontaneously while traveling through what is normally considered empty space, a behavior strictly prohibited under Lorentz invariant theories. Similarly, high-energy photons might decay spontaneously into lower-energy particles, a phenomenon known as photon decay. Detecting either effect at the FCC would provide compelling evidence that the invariant speed of light is not fixed, but energy or wavelength dependent. Such a discovery raises profound questions. Would confirmed Lorentz violation require abandoning relativity entirely, or simply modifying it? Lorentz invariance is deeply tied to the causal structure of quantum field theory. Violations of this symmetry, or of associated CPT symmetry, carry major implications for the logical and causal structure of the universe. If FCC experiments revealed that particles could exceed the speed of light, traditional relativistic physics would face significant challenges. Theoretical frameworks allowing faster-than-light motion or fundamentally non-local physics would gain traction. This potential breach of the relativistic light cone implies that under extreme energy conditions, energy or information might propagate in ways that violate standard temporal sequences, creating paradoxes and demanding a complete rethinking of quantum gravity. The consequences for cause and effect, the fundamental ordering of reality, are staggering. At these extreme energies, events could precede their causes, and information could travel backward in time within certain reference frames. Predictive power in physics would diminish as temporal ordering becomes ambiguous. Engineering a collider capable of probing such phenomena requires a massive technological leap beyond the LHC. While the LHC operates in a 26.7 kilometers tunnel with a maximum collision energy of 13.6 TeV, the FCC-H leak designed for a 90.7 kilometers tunnel, aiming for proton-proton collisions at 100 TeV. This nearly tenfold energy increase is essential because effects of Lorentz violation are hypothesized to grow with particle energy. The engineering challenges are immense. Tunnel access shafts must reach depths of 180 to 400 meters. Beam stability at 100 TeV demands advanced research into next-generation superconducting magnets, including high-temperature superconductors, and the preparatory phase for construction may take 20 to 30 years. Even with such high collision energies, detecting a subtle spacetime flaw is complicated by the sheer volume of data. FCC-HHH could produce up to 1,000 proton collisions per bunch crossing, requiring detectors to function under extreme radiation levels. Unlike new heavy particles, a spacetime anomaly would appear as a slight statistical distortion in particle kinematics, often in low-momentum regions of phase space, making it extremely challenging to identify. This necessitates highly specialized model-independent detection techniques. Unsupervised machine learning systems are being developed to flag events that deviate from standard model predictions, regardless of their specific nature. One example is the decorrelated anomaly detection method, which uses quantile regression to ensure anomaly scores remain independent of primary trigger observables. This approach is crucial because a spacetime flaw is expected to produce subtle, diffuse distortions rather than obvious spikes in energy spectra. Traditional collider triggers that focus on high-momentum events are essentially blind to the subtle signatures of a spacetime anomaly. If a future collider were to detect such a flaw, it would likely be through advanced AI systems capable of identifying patterns that human-directed searches could never anticipate. This represents a paradigm shift. In conventional particle physics, experiments target specific phenomena, supersymmetry, extra dimensions, or predicted new particles. A spacetime error does not fit any of these templates. It is not a particle, but a systematic deviation appearing across thousands of processes. Human physicists cannot monitor all possible kinematic distributions simultaneously for such minute anomalies, but AI systems can. These algorithms learn the expected behavior of standard model physics and flag deviations automatically, revealing the anomaly not by seeking it directly, but by recognizing that something is off. If Lorentz symmetry were violated, the focus of research would immediately move from effective field theories to the domain of quantum gravity, forcing physicists to confront the underlying structure of spacetime at Planck scale energies. Both major approaches to unifying quantum mechanics with gravity, loop quantum gravity and string theory, predict that Lorentz violations could arise near the Planck energy. Given the vast gap between the FCC-Sh's 100 TeV collisions and the Planck scale, any detectable effect would need to be either strongly amplified or associated with the highest dimensional operators in the Standard Model Extension, SME. One compelling theoretical source for a spacetime anomaly is the concept of quantum foam, proposed by John Wheeler. Below the Planck length, 10⁻⁵ meters, and Planck time, the smooth continuum of spacetime described by general relativity is expected to break down. Instead, spacetime would consist of countless tiny fluctuating regions with foam-like quantum behavior. These microscopic fluctuations could manifest as measurable deviations from smooth spacetime at macroscopic scales. Loop quantum gravity, for instance, models spacetime as fundamentally discrete, composed of spin networks or spin foams. Such discreteness directly conflicts with the assumption of continuity required by Lorentz symmetry. Confirmation of Lorentz violation at the FCC would therefore support the idea that our familiar four-dimensional spacetime is emergent, built from granular fundamental components. The implications for competing quantum gravity theories are profound. Certain string theory models, especially those involving quantum foam or supercritical regimes, naturally allow Lorentz and CPT violations. These scenarios often describe our universe as a four-dimensional brain, embedded within a higher dimensional bulk, where quantum gravitational effects leak through and induce subtle symmetry breaking. Loop quantum gravity, meanwhile, predicts a discrete spacetime structure, but achieving effective flat space solutions remains challenging. Some analyses suggest that spin foam discreteness could generate Lorentz violations exceeding current experimental bounds, acting almost like a modern analog of the 19th century luminiferous ether, interacting with matter and carrying entropy. A confirmed Lorentz violation at the FCC would significantly boost the credibility of discrete spacetime models while challenging smooth spacetime frameworks. In essence, a single detection could determine whether spacetime is continuous or granular, a decisive test for quantum gravity theories. Spacetime anomalies are also intimately linked to the existence of extra dimensions. Many theoretical attempts to resolve standard model issues, like the electroweak hierarchy problem, rely on extra-dimensional frameworks, such as the Randall-Sundrum model. In this scenario, gravity propagates through a curved, compactified extra dimension, while standard model fields remain confined to a four-dimensional brain. If the FCC detects a spacetime anomaly, it might coincide with the production of Kaluza-Klein gravitons, massive excitations that reveal the geometry and scale of extra dimensions. With 100 TeV collisions, the FCC-H could reach 5 sigma sensitivity for Kaluza-Klein states up to roughly 4 TeV, far surpassing the LHC's capabilities. Observing both a space-time anomaly and Kaluza-Klein gravitons would provide a coherent picture, suggesting that the anomaly reflects the underlying higher dimensional structure of our universe, not just a local quantum effect. Finally, the search is constrained by astronomical observations. Despite decades of terrestrial experiments, no compelling evidence for Lorentz violation has emerged in astrophysical data. Detection at the FCC would therefore represent a groundbreaking confirmation, revealing phenomena previously invisible to current instruments. The most stringent limits on many SME coefficients come from observations of extremely high-energy astrophysical events. Gamma-ray bursts, for instance, provide a natural laboratory. Photons with energy spanning a wide range travel billions of light-years, and their near-simultaneous arrival constrains possible modifications to dispersion relations. These observations impose exceptionally tight bounds on CPT and even Lorentz violations, improving sensitivity in some sectors by factors ranging from 10 to 100,000 compared to previous measurements. Similarly, ultra-high-energy cosmic rays, such as pions reaching Earth with energies up to 30 TeV, provide strong constraints on possible deviations in particle velocities. The absence of certain absorption or decay processes places two-sided limits on Lorentz invariance violation. If the FCC-H were to detect a clear space-time anomaly at 100 TeV, this would present a major paradox. How could such effects appear in a terrestrial laboratory when astrophysical data over billions of light-years show near-perfect adherence to Lorentz symmetry? There are 3 scientifically grounded explanations for reconciling this tension. First, chirality or coupling specificity. The Lorentz violating coefficient detected might only affect specific interactions or decay modes of heavy particles produced exclusively at 100 TeV, invisible at lower energies. Second, fine-tuned directionality. SME postulates fixed background fields defining a preferred frame
of reference. The measured signal could depend sensitively on the experiment's orientation relative to these fields. The FCC's location, tunnel geometry, and precise timing could coincide with a maximal sensitivity axis. Third, higher-order SME operators. Astrophysical constraints mostly test lower-order operators, whereas 100 TeV collisions may excite higher-order terms suppressed in astronomical observations. The FCC could therefore access energy scales required to reveal these otherwise hidden effects. Another major consideration is vacuum stability. The standard model faces the electroweak hierarchy problem. The Higgs mass is highly sensitive to quantum fluctuations up to the Planck scale, requiring extreme fine-tuning. Current measurements suggest that our electroweak vacuum is metastable rather than perfectly stable, meaning it could theoretically tunnel into a lower-energy true vacuum, with catastrophic consequences for matter and fundamental constants. Detection of Lorentz violation would directly inform the fundamental cutoff scale of the standard model, potentially resolving the hierarchy problem either by introducing new stabilizing fields or by placing the Higgs potential at the precise boundary of stability, a scenario known as criticality. In this sense, the search for Lorentz violation and beyond standard model particles is not merely academic, it addresses the universe's very stability. The implications extend to dark matter and dark energy as well. The standard model accounts for only about 4% of the universe's mass energy, leaving dark matter and dark energy largely unexplained. The SME framework includes Lorentz-violating corrections in the gravitational sector, meaning a confirmed space-time anomaly could provide an empirical link to these missing components. If space-time and gravitational symmetries are explicitly broken, this flaw could underlie cosmological fields associated with dark matter or dark energy. The FCC's 100 TeV collisions would provide unprecedented sensitivity to simplified dark matter models, offering a unique opportunity to probe these interactions. A confirmed space-time anomaly, therefore, would not be an isolated discovery. It could simultaneously illuminate fundamental particle physics, the nature of dark matter, the origin of dark energy, and the solution to the cosmological constant problem. In effect, fixing space-time might unlock multiple cosmic mysteries at once. Such a confirmation would trigger an immediate theoretical crisis. The foundations of modern quantum field theory rely on the CPT theorem, which guarantees that particles and antiparticles share identical properties if the theory is local, Lorentz invariant, and respects spin statistics. Observing a space-time flaw would challenge these core principles, forcing a re-evaluation of fundamental assumptions that have underpinned physics for decades. If CPT symmetry were violated, it would imply that our current theories must be fundamentally non-local or non-Lorentzian, demanding a radical overhaul of the entire theoretical framework. A strong Lorentz violation signal would directly challenge the speed limit imposed by special relativity. If such an anomaly indicates that matter can exceed the speed of light, maintaining causal structure becomes profoundly difficult, particularly regarding causal equal-time commutators. Under extreme conditions, like 100 TeV collisions, the boundaries of the relativistic light cone could be locally breached, allowing energy or information to travel backward in time within certain reference frames. Resolving this causal crisis would require defining new energy-dependent causal cones to preserve logical consistency. This is not a matter of tweaking equations or applying minor corrections. It demands a complete reconceptualization of space, time, and causality at ultra-high energies. Existing textbooks, models, and assumptions would all need to be reevaluated. The timeline for the FCC program spans decades. The precision-focused FCC-E phase is scheduled to begin in the late 2040s, while the high-energy FCC-H phase will start around 2072. That puts definitive answers roughly 50 years in the future. But the search for space-time anomalies begins immediately. Current LHC data is being reanalyzed within the SME framework for subtle hints, while astrophysical observations continue to constrain possible Lorentz-violating coefficients. In parallel, theoretical models are being refined, and construction efforts, tunneling, magnet development, and detector design are steadily progressing, bringing us closer to the moment when 100 TeV protons collide and either confirm spacetime's perfection or reveal a hidden flaw.
If a space-time anomaly exists, it represents the ultimate boundary of current physics. Beyond it lies quantum gravity, discrete space-time, modified causality, new insights into dark matter and dark energy, and a fundamentally different understanding of reality itself.
Particle colliders were originally built to discover new particles. We found the Higgs and validated the Standard Model. Now, the next generation of colliders aims to uncover something far deeper. Not a particle, but a structural asymmetry, a break in the perfect symmetry that was assumed to govern everything. The discovery of such an anomaly would redefine physics. The mathematics indicates it, quantum gravity predicts it, and soon, with a sufficiently powerful collider, we may prove it. Reality is not what we imagined, and we are on the verge of discovering what it truly is.